Probably Jacob Bernoulli. That guy. He got everything. What's that? The Bernoullian?
Probably there's 6 other.
Because there's a lot of other Bernoullis, and they were all very competitive and jealous. All right, so we need the Jacobian.
6 other Bernoulli majors.
All right. So just evaluating this at x, at the general point x, y. This is not. I'm not evaluating it at 0, 0 yet, but just at the random point x, y. So I'm going to kill some of the notation. Just f sub x. That's the partial with respect to x. F sub y. G sub x. G sub y. I'm dropping the x, y just for time. All right. So I look up there my function f. And to differentiate this with respect to x, I treat x as the only variable, and we just assume y is a constant, some fixed value. So we take y to be a constant, and x is the variable. So when I differentiate this with respect to x, what do we get? 1, that's 0. And, if I move that x over there, then the 2y is just the coefficient of x. And right, derivative of that is just 2y. So I'm going to get 1 plus 2y. All right, now partial of f with respect to y, that's gone. That's negative 3.
Negative 3 plus 2x.
And yeah, that's linear in y, so the coefficient would be 2x. And that was negative 3 plus 2x right here. So that whole term, that whole thing is the second component. Now, moving on to the function g, partial with respect to x, I'd have a 4. That term is 0. And with respect to x, I just get y.
Oh.
Minus y. Right?
Is it, when you were saying for the invertible and determinant, is that where the determinant is identically 0 or just
There's
at
only
the
one
point?
determinant. The determinant's not a function.
Oh, but I meant if you could do the determinant for every point in this whole function by doing
You
this.
can find, okay, yeah. You can find this, but then you're going to have, again, a function of x and y.
Sure.
You can find, I guess
But
you
it could be,
compare that.
it could be identically 0 at every point, but I guess that's
But you
probably
would know
really
that that would take a lot of work.
Sure.
And that's
So it's
probably
just
not
at the
gonna
one
happen.
point
Yeah.
that we're testing.
We are going to evaluate it at 0, 0, and that's quicker to see, oh, is this invertible or
Yeah,
not?
sure.
As opposed to doing it as the pure Jacobian and finding all the ordered pairs x, y that make that determinant 0 and throwing
Sure.
those out. It's going to be quicker to find the critical points by solving those, putting those two equations to 0, finding the critical points, and then evaluating the Jacobian at those particular points.
Okay.
Because then they don't have to worry about the rest. All right, so last one, we were on the function g differentiated with respect to y. So with respect to y, that term's dead. Here I get a minus 6. And here I get, with respect to y, I just get the x, so minus x. So there's the pure Jacobian. Now we evaluate it at 0, 0. That's our critical x naught, y naught critical point. So at 0, 0, the Jacobian is just going to be a matrix of numbers, real number elements. So put in 0, I love putting in 0 for all these because all those terms drop out. I get 1, negative 3, 4, and negative 6. Okay. Now, so that is the matrix, the coefficient matrix of the linearized system. Okay? All right. So the linearized system near that critical point 0, 0 is, I can write it this way, u prime equals that Jacobian evaluated at the critical point 0, 0 times the vector u. Okay? All right, so that Jacobian becomes our coefficient matrix. It's just 1, negative 3, 4, negative 6, and u is U and V. So it just takes it to a U and V system, UV plane. Okay. So that's our Jacobian, and we look at we find its eigenvalues. All right. So at this point, hopefully, this is becoming clear. So the eigenvalues come from when we set the determinant, and this is not A anymore, right? It's J minus lambda I.
Don't those variables U and V have primes on? The ones on the left.
Oh, the ones on the left, U. Yeah, that's U prime. So that's a matrix or the vector of derivatives. Okay. So I'm going to get a minus lambda in each of these diagonals, and the determinant of a 2 by 2 product of that diagonal is going to be 1 minus lambda times negative 6 minus lambda minus the product of the other diagonal. That's negative 12. Minus negative 12 is the same as plus 12 equals 0. And I hate all those minus signs. What I do is pull out a negative from each of those. That would be lambda minus 1. Pull out the negative from that one. It would be 6 plus lambda. That's the same as lambda plus 6. Equals 0. Let's refactor this. We're going to have lambda squared plus 6 lambda minus lambda. So that's going to be plus 5 lambda minus 6 plus 12, that'll be plus 6 equals 0. All right, and this does factor. Plus 3 plus 2. All right, so we can, they're usually nice enough to give us these ones that factor, give us whole numbers. So the eigenvalues of this Jacobian matrix, negative 3, negative 2. Okay. And these are both, they're real, they're unequal, and they have the same sign, both negative. All right, now, not always can we make the same conclusion about the linearized system than we can from the linear system. There's some small, we'll talk about those, but there's a new table for this. Page 393, the linearized system. And 0, 0 was the point of interest. What is, on the top of 393, there's a table. So the eigenvalues are they're both real, unequal, and negative. Right, stable, improper node. Okay. All right. So it helps. Yeah, we can take a nearly almost linear system, convert it using the Jacobian to a linearized system, and in most cases, the critical points here have the same characteristics as the critical points of the original. Okay. Of course, the critical points of this linearized system will always carry to 0, 0, but this talks about the original. Okay. And in this case, the original one was also 0, 0. All right. So let's do another one together. All right. Here we go. Here's one that's not linear. Okay. So it's not too bad to find the critical points of this one, because notice the first equation, that expression on the right doesn't involve x. So if you set both of those to 0 and you look at the top equation, what are the solutions for y there?
1 and negative 1.
1 and negative 1. If you take those one at a time and sub them into the other and set it equal to 0, corresponding to y equals 1, you'll get x equals 1. Corresponding to y equals negative 1 from the top equation, you'll get x equals negative 1. Okay, so we have two critical points, and only two in this system. So our goal is to categorize each critical point of this original system. Okay, but first we're gonna transform it. Okay, we're gonna linearize the system. So we need its associated Jacobian. And let's do that. So Jacobian, just at a random point x, y, will be what? I need to do, let's write it down. This expression right here is my f of x, y. This one is my g of x, y. So the Jacobian, partial of f with respect to x, partial with respect to y, and then g with respect to x and with respect to y. All right, so what do we get? So take f, partial with respect to x, what do we get? 0, right, because that's a constant with respect to x. We get 0 minus 1, minus 0, so we just get 0. Now what's the partial with respect to y? 2y minus 0. Okay, and g, with respect to x, I get 3x squared minus 0, so just 3x squared. And partial of this with respect to y, first term is gone, that's a constant, so 0 minus 1. Okay. All right, so let's find, at 1, 1, we're going to look at that, at this point, this critical point first. At 1, 1, the system looks like u prime equals Jacobian at 1, 1, and that's a matrix, times the u vector, that's in matrix form. So what does it look like when I evaluate this matrix at 1, 1? 0, 2, 3, negative 1. Okay, so that's my Jacobian, and u and v, if I break out that vector, it's just the vector of components uv right there. Okay. Yeah.
So, this one actually can't tell us the general form of the equation. This will just tell us whether or not what the critical points look like.
Yes.
So we're just using the linearization because we can't find it at the actual point. So the linearization gives us an approximation.
It's going to be correct, except in a couple sensitive cases, and the book talks about that. The sensitive cases are when the eigenvalues are equal. That little nonlinear bit that we disregard at the error term, that small difference could create a difference in the coefficient matrix.
Sure.
That it would maybe not have equal eigenvalues. Okay. So in that case, we call that it's called a bifurcation, when something is at a point, a balancing point, where a small difference could split it into two different cases.
Gotcha.
So when the eigenvalues are equal, that's a very sensitive case, because that small nonlinear bit that we disregarded could make the actual coefficient matrix different, and I would have different eigenvalues. And if they're not equal, then we have a very different categorization of that point.
Sure.
Okay, so that's one sensitive point, is when the two eigenvalues are equal. The other sensitive one is when we have purely imaginary eigenvalues. So real part 0 plus or minus vi. Okay, it talks about that later on in the book. But so this system, I could write it this way: u would be u prime would be 0u plus 2v. This is just the corresponding linearized system in the uv plane, and v prime would be 3u minus v. Okay. All right, now let's find the eigenvalues of this matrix So when we find eigenvalues, determinant of, j minus lambda I, and it's going to look like, the equation will look like negative lambda times negative 1 minus lambda minus 6 equals 0. All right, now I hate all these negative signs, so what I'm going to do is that's the same as lambda. If I take out a negative there, that's just going to be 1 plus lambda minus 6 equals 0. So this is going to be lambda squared plus lambda minus 6 equals 0, and I think this does factor. What is this? Plus 3 minus 2. So the eigenvalues, negative 3 and negative 3 and 2. All right. So look on page 393. These are unequal. Again, real, and they have opposite signs in this case. So what does that give us?
Unstable saddle point?
Right.
Is there a saddle point?
No, yeah, every saddle point is unstable. So we get a saddle point. This is a saddle point of the linearized system. And that's not one of our sensitive ones. The two sensitive cases where you can't really determine exactly what kind of critical point it is if the eigenvalues are equal, or if they are purely imaginary, 0 plus or minus bi.
To some extent, does this matter on the parameterization of x and y? Because, for example, if they're parameterized with respect to t on a very large scale, then a difference of like 1 could end up being a really small difference and throwing things off, or no, is that not really an issue?
I'm not sure. I'm not sure if I can answer one way or the other for certain. All right, so let's look at the second page, -1, -1. We still got the same Jacobian matrix at the general point x, y. Jacobian matrix here at -1, -1. We've got to watch our signs. Put -1 for x, -1 for y. The Jacobian would be 0, -2, -1, but I'm squaring it, so I'm going to get 1 times 3, so I still get 3 there, and -1. Okay, so that's the Jacobian matrix there. And so our system, it says we have a linearized system in U and V. Our system would look like U prime equals Jacobian -1, -1 times U bar. So in other words, U prime V prime equals 0, -2, 3, -1 times UV. Okay. All right, and if you want to write it all the way out in component form, it would be U prime equals 0U minus 2V. And V prime would be 3U minus V. Okay, so you can see our coefficient matrix right there, if I put it as 0U, right? So let's find the eigenvalues of this guy. So it's going to be 0 again in that diagonal minus lambda, so negative lambda times -1 minus lambda minus product of these guys, that's -6. So this gives me a +6, isn't it? Equals 0. This will be lambda squared plus lambda plus 6 equals 0. All right, so this guy, Doesn't factor. Plus 3 minus 2 doesn't work because I got a positive, it's a plus 6. It does not factor, we have to maybe resort to the quadratic formula. Lambda is equal to the opposite of the middle coefficient, the b coefficient, so -1 plus or minus b squared minus 4 times a times c, 1 times 6, and it looks like we're going to get complex O over 2 times a, the leading coefficient. All right, so that gives us -1 plus or minus square root -23 all over 2. And if we break that down a little bit further, we just got -1/2 plus or minus, well, that's going to be I times root 23. Root 23I over 2. So these are complex. The real part is there. The real part of this number does not equal 0. So it's a true complex. Complex with negative real part. All right. So we talked about this last time. If you have a complex, it's going to, well, if it's imaginary, it's going to involve sine and cosine, right? That would be just like a spiral. Okay, but if I have a real part, then we have the power of e out front, e to the real part times t. And if that real part is negative, I have e to the -1/2 t. That would be a dampening effect on the both x and y. So I'm thinking we are going to have a spiral. And since the real part is negative, it's going to be spiraling towards 0, 0.
Or negative 1, negative 1.
Oh, well, in this system, in the UV system, it's going to 0, 0,
okay.
right? But -1, -1 is a spiral? Stable spiral, is that what I said? Stable spiral, and stable meaning that it's a sink. I always get those mixed up, source sink. But it's a sink. All the trajectories will be swirling in towards -1, -1. Now I think I made a mistake on this first one. We're categorizing 1, 1. This is a saddle point of the original system. 1, 1 is not a critical point of the linearized system. 0, 0 is. That 0, 0 corresponds to the critical point of 1, 1 in the original.
So now we know that, the reason you were saying that if it was, so basically sinks, we will, if we're close to them, it'll still go into the sink, but if it's like a sorter, and you're close to it, linearization might not work because it could fall off, if it's not really close to it, it won't tend towards the hole.
So look what's going on. So we categorized, here's the original. This is the original nonlinear system. And I put enough trajectories in here to show both of them. We had 1, 1, that's right here, and you can see that is what kind of critical point? Is a saddle point. Okay. And we did 1, 1 first. Yeah, we did 1, 1, and we got a saddle point. Okay. Now, what's interesting is that this is the original system. It shows both. The transformed system, the linearized system, is right here. That saddle point is carried to 0, 0. 0, 0 of the linearized. So it carries it to 0, 0, but look at the behavior is essentially the same. Under, certain conditions, all that. And now, what do we get for the other critical point, -1, -1? Stable spiral. And obviously, we can see that that is the case. I could have just graphed this without doing any just graphically, I could see that that's a stable spiral. We did the work. We got a stable spiral of the linearized system. And here is that one and it carries it to 0, 0. And it has the same behavior. So it carries it to 0, 0, but it's still a linear spiral. And it's stable. It's in a sink. You can see all the arrows are bringing it inward. So that would be the direction of travel of each of these trajectories, inward. Okay.
What do we use this for?
Oh, that's going to be in 6.3. Now remember that these are functions x of t, y of t. We're graphing this in the x, y plane so that t is the invisible parameter. Time, at any point on a trajectory corresponds to a specific time, and time is going forward as this approaches the scene. X and y itself, what's happening to the x and y values themselves? They're both approaching 0 and oscillating, right? Just like we did if we actually solved explicitly and found the solutions for x and y in this system, or in this case, u and v. But those functions would be oscillating themselves. So this is putting them both together on one plane. Okay. Oh yeah, one other thing I wanted to note. Yeah, linearization carries each critical point of the original system to 0, 0. We analyze it there in the UV plane. Okay. We will look at some applications of where this comes in.
Because it seems like one's going to be affecting the other. If you're looking at it in the first figure, but in the second figure, they're just indistinguished.
In which one? Down here?
For comparison to the top,
Mm-hmm.
the bottoms, the tops, the two critical points are affecting each other. And in the bottoms, they're just by themselves.
Well, a specific trajectory could go towards that unstable saddle point, deflect away from it, and then become stuck in that sink. That could happen. Mm-hmm. Sometimes these are called orbits. Those trajectories, just the set of all points. If I dropped a point down in here, the orbit is the set of all points that it would traverse. But yeah, certainly one could be near that both critical points. Some of them won't go into either of them. There are trajectories that go around that sink and end up going around the other side of that saddle point. All right. So what I want to show you again, another reason to use technology. I'm just going to put in the original. What was that original system? Y squared minus 1, x cubed minus y. All right. So y squared minus 1 and x cubed minus y. And we just had -1, -1, and 1, 1. So I should be safe, maybe 3 to 3. All right. So here, and it's very hard to tell what's going on because you can't see, right? These, we talked about last time, the length of these vectors represent the speed, the magnitude, the speed at which the trajectory is being traced out, because those are velocity vectors, the tangent vectors of the trajectory. So when they get very, very small, that's where dx dt, dy dt are nearly 0. And we can put on these, here we go, at -1, -1, that was our spiral. This is it being created, yeah? Okay, at 1, 1, yeah, we get these things, we'll see how it's repelling away from it. That's the saddle point. The other thing about this that I didn't include on here, very powerful, I can graph x versus t explicitly. So say I take this trajectory, click on it, that's what the curve looks like in the xt plane. Okay. It goes out to 0 as t goes to infinity, but see how it oscillates? It's negative, positive, negative, a little bit more positive, but eventually it goes to 0.
Is that x or x prime?
This is a graph of x right now. This is a graph of x versus t.
Okay.
The solution to the system.
Oh, so the -1, I see, the
Right.
spiral points.
Yeah, I could also have chosen, to graph the y coordinate versus t. This is the y function separately, but graph explicitly a negative t. That's what it looks like. Oh, the y is positive for most of the time. Then it goes, looks like it's settling towards -1. That's
Yeah.
weird. The y, oh yeah, the y coordinate, of course. Of course the y coordinate is settling towards a -1. Look at that.
So was the x coordinate.
So was the x, right. In the UV plane, they're going to both to 0.
So,
But here, this is what's more awesome.